This program looks at ionization energy. I'd like to begin by reviewing a few principles of Bohr's model of the atom. First of all, as electrons move to inner orbits, they release energy in the form of light. Here, an electron falling from the second orbit to the first would give off a particular photon of light, more than likely in the ultraviolet range. Here, falling from the third orbit into the first orbit, we get off a different wavelength of light. This one would contain more energy because the fall is greater. That would be shown by a shorter wavelength. So the wavelengths change as our electron falls through more distant orbits. The orbits tend to converge as we get to higher energy levels. This is called the convergence limit. So as we move out from the nucleus, our orbits get closer together. Their energies get closer together. So there becomes less and less change as we move out. But not only does the energy change become smaller, other properties, such as the change in the wavelength and change in frequency, also become smaller. Finally, as electrons move to more distant orbits, they absorb energy. Here I'm showing the transition that would happen when we ionize the element hydrogen, taking its electron from its first orbit out to its convergence limit. Ionization energy is the energy required to remove 1 mole of electrons from a gaseous element. So essentially we're taking the electrons out to the convergence limit. In the case of hydrogen, the equation would look something like this. Here I'm showing the wavelengths that are given by hydrogen transitioning from the nth orbit to the first orbit. So we can see that the wavelengths are becoming smaller. But not only that, the differences between them is becoming smaller, as predicted when we approach the convergence limit. If we make a graph of the wavelength and the change in the wavelength, we'll see they'll cross the axis at this particular point. This would correspond to our wavelengths of light that would be given off as an electron transitions from the convergence limit to the innermost orbit, in case of hydrogen, the first orbit, and that wavelength, 94 nanometers. I'm going to use that now to determine the ionization energy of hydrogen. First off, let's find the frequency of that particular wavelength. So there we have the wavelength and this equation from our IB data booklet. The speed of light is equal to the frequency times the wavelength. Speed of light we can get from our IB data booklet and then solve for our frequency. So 3.19 times 10 to the 15th seconds to the minus 1. Now I want to determine the energy associated with this photon of light. That's given by this relationship, also in our IB data booklet. E is equal to Planck's constant times the frequency. Planck's constant is also available in our IB data booklet. Substituting in the value for Planck's constant and our frequency from the first part above, we can determine the energy of our single photon, 2.11 times 10 to the negative 18 joules. Now I'd like to determine the energy for 1 mole of photons, since ionization energy refers to the energy of 1 mole of electrons. So I take the energy associated with 1 and multiply it by Avogadro's number, and I get 1.3 times 10 to the 6 joules, or 1300 kilojoules. Remember, questions are always welcome. Thanks for watching.